Do you hear me? Thanks. Alright, so sorry for being late. Let's start with a simple different topic, but you will see why I like to mention the atmosphere. So you know the atmosphere is a pretty complex something. It's mainly composed of nitrogen, oxygen, argon, carbon dioxide, and other gases, but all these gases have very small concentration in the atmosphere. Why do we have atmosphere? Why is it important? Because perhaps you know there are high energy particles coming from the universe, not only from the sun by the solar wind, but also there are lots of other particles, and they interact the upper side of the atmosphere and create secondary particles, but sooner or later they will decay and they won't hurt us. So the atmosphere like a shield. One danger thing is the solar wind. Sun can emit very large amount of charged particles, and it's shielded by the atmosphere. It's not something which is only for the Earth. Also the Mars has atmosphere, but you can see the differences. It's very thin. It's mainly made of carbon dioxide, but of course it's not good for living organs. But if you can bring enough plants or anything else that you can use to convert carbon dioxide to oxygen, it can help for the first Mars colonies to have enough oxygen. On the Mars it's very thin. Also the pressure is much lower than at the Earth, only 1% or less than 1% of the Earth. What can we measure from the atmosphere? We can measure the pressure. The pressure is something you can imagine. So if you have for example, a square meter area, the pressure from the atmosphere is technically the weight of the vertical column of the atmosphere above that surface. It's huge amount of air or gases. So this is why we had the one atmosphere, which is 10 to 5 Pascal. The first barometer was the mercury barometer. You can see on the plot. So if you have mercury filled tube, and if you put upside down in also a mercury filled volume, the pressure from the atmosphere is the blue arrow, and the pressure from the mercury inside the tube must be balanced, and from a scale on this tube you can read out what is the height of the mercury, which is equivalent with atmospheric pressure. And at that time that was 760 mercury millimeter. This is why we still use this old-fashioned unit. If you see some other barometers, you can see they use this TORR, which is mercury millimeter equivalent quantity for the atmosphere. Why is it important? The pressure on the surface of the Earth and the weather has a very strong connection. You can imagine if you have a warm air that rises up, the pressure will be lower because of the motion of the air. And if this air is full of humidity, and since it goes to the upper region of the atmosphere, which is colder. It reaches the 100% in the humidity, and that means from the air, clouds are created. The upside down direction is the dry and cold air can go towards the surface of the Earth. That means it increases the pressure, like pushing the surface of the Earth. This is the high pressure area. And this low pressure and high pressure area, if we measure, it can help us to forecast the weather, or at least describe the condition of the weather. If you see a weather forecast, you can see this low and high pressure area. These are cyclones and anticyclones. Alright, so if something which is useful for weather or only observing the atmosphere, even with a very cheap setup, like let's say what you can see here is €50, you can measure the atmospheric pressure with pretty precisely, this plus minus 0.2 Pascal. These are sensors, so if you are interested in, I can create a setup for the seminars and you can play with. But most of you should have a phone that also can measure the pressure. So you can see the pressure sensor, this BME280, is on the left side of this plot. So this purple PCB, that's pretty small. You can put the sensor also in your phone, and you can measure the pressure by that. So with all of you, we will do this atmospheric pressure measurement to play with data. What do I mean data analysis? So in physics, we want to measure things, which is important for other things. Right now, let's say we want to measure the pressure. How can we use that? If you were at the seminar, I mentioned that there is a so-called Firefox application, and if you choose the pressure on its main board and you walk up and down a stair, or down or up, it's up to you, we could measure how the pressure changes. From the literature, we know that not inside the building but outside the building, when there is nothing, so it's in a very quiet situation, the pressure close to the surface of the Earth changes 1.2 kilopascal for every 100 meters. With your phone, you can measure it, and you can see, you can validate this number. So we don't have to believe any of the literature. If we can measure something, we can also have our own idea how, for example, this pressure changes. So we will do it again on the seminar, but you can do it at home also. Use the Firefox. Since the Firefox measures the pressure at given time, you also have to convert the time to meter. What I mean, at the beginning we wait a bit on the bottom of the stairs, then we walked up. Here you can see seconds, but we have to convert it for a meter because I want to know how the pressure changes in every meter. So you have to measure the height of the stairs and say, here we have at, for example, 0 meter, and here you can see in the next slide, here we were at 3.5 meter. So please also measure the stairs, the height of the stairs, and convert the time to meter. We waited a bit on the top of the stairs just to recalibrate our sensor again, and walk down and then wait. You can do that game at home also. What can we learn from this one? At the first, let's say, bit more than 10 seconds is the calibration. I zoomed in. You can see even we didn't move, the pressure changes. It can be because of our stability or handshake, or it can be the noise from the sensor. But independent of the source of this noise, these uncertainties, these errors are not only at the calibration, but these are always during the measurement. These are always there during this measurement. So it's important to analyze the first few seconds to have some estimation about the precision of the setup. Setup means phone, data acquisition, or hands, or even there can be wind. Even you don't feel it, small winds can change the pressure also. So how can we analyze this data? So we should say something for the uncertainty here. We will do it in the seminar, but we are looking for the standard deviation. Let me show you some other representation. So if you enlarge the PDF, I hope you can download, you can see here the numbers. These numbers are these orange points here. Here you can more or less see its standard deviation, so it's how it differs from the mean. But you can create a plot like this. This is the so-called density plot. If you measure, I see only the last two numbers. If you measure 61, you can add an entry here. If you measure 63, you can add an entry here. You can see we have much more 63 than 61 or 65. So if you collect all the measurement, it shows a peak-like structure. This peak-like structure says most of the measurement is mainly between 62 and 64, so it has a middle, a central, but we have some tails with less entries. How can we quantify the uncertainty? Perhaps you didn't hear about Gaussian distribution, but we also can talk about this. If you fit this distribution, this density plot with Gaussian distribution, from the parameters of the Gaussian distribution, you can read out the mean. On this upper right box, you can read out the mean and also the sigma. The sigma is 0.76. Let's say this is 0.8. So what I can say, this Gaussian distribution has a mean close to 63 and it has a sigma. Sigma is a good number to describe the error, and we should suppose that this uncertainty, the 0.8 uncertainty, or we can say 1, which is, you see these here we have pascals, so the mean is 99563 Pascal and the sigma is 1 Pascal. That means anything you measure in this range will suffer from this 1 Pascal uncertainty. Alright, we know it. Let's go further. When I walked up, now I enlarge this area from time 13 to time 30. But I do not show the time, but I show the height, my position on the stairs. The height can be calculated by counting the stairs and measuring the height of one stair. And you can say from 0 I went up to 21 times 16.5 centimeter, which is more or less 3.5 meter. Then I fit it with a line. If I fit a line, I did it in Excel, I can have the gradient of the straight line. What this gradient says: if I move from 0 to 1, if I move 1 unit on the x-axis, the y changes by minus 11.4. What it means? It means if the pressure changes minus 11.4 in every meter, that means, what was the question? That means in 100 meters, it changes not exactly 1.2 kilopascal, which is 1,200 pascal, but if you multiply with this number with 1,000, it will change by our measurement. So this is not a number from the literature, this is our measurement. It changes 1,131. How precise is this number? So this is why we did this calibration. I can believe this number with plus minus 1 pascal. And what it says, since this plus minus 1 also contains the 12, we can believe this number. So the pressure as average value, it's true that it can change 12 pascal in every meter. So you can see the way how we do the measurement. We calibrate our system, we measure something, and in the end, the final answer can be done only by the measurement and the uncertainty. Let's say, for example, if I have a very precise device with 0.1 pascal precision, I won't believe this minus 11.4, because minus 11.4 plus minus 0.1 is also the minus 11.3 to minus 11.5. So the 12 is not in this interval. This is why it's so important, because with the uncertainty, you can set up an interval where you believe the result, and with that interval you can say yes or no for the result. Alright, so that was something we will do several times on the seminar. Calibrate things, measure things, and say something as final result. Let's go back to the motion. And by the way, please check this file, folks. Check your phone, and if you have pressure measurement, find the stairs, do some measurement, and bring it to the seminar. You can export in Excel the data, and with the Excel you can play that game. We will do that game until you feel able to do it alone. Alright, projectile motion. Projectile motion is a very simple motion, not that simple like free fall, but pretty simple things. Instead of the 3D, we will use only 2D. And in this 2D, we can separate the motion. In the y direction, this is a free fall, and in the x direction, this is a motion with constant velocity. There are two things as boundary conditions, so there is no air resistance, and the acceleration is g, and it directed downward. From this example, we can calculate several things. We will add the initial velocity, initial height, the angle of the motion, this alpha, the launch. From that one, you can calculate the horizontal and vertical velocity only by using sinus and cosinus, and you can calculate the distance, the maximum height, and the time of flight also. Let's see how. So, for this motion, I said at the very beginning, we also have to set up a coordinate system. We should set up a coordinate system which can help to solve the example. So in this projectile motion, we say the x is to your right and y is upwards. And from this coordinate system, we know the ay, the acceleration on y, equal minus g, since the g goes downward, so it's minus 10, and the ax, since there is no air resistance, it should be 0. for this example, let's say we started from the origin. So the x initial, y initial is 0 and the original speed is v initial, and there is a theta initial angle. What are the boundary conditions? You can see it on the left. So x and y initial equals 0. The initial speed along x and along y is vi cosinus theta and vi sin theta. And from the nature of the motion, we can say, since there is no air resistance, ax is 0 and ay is minus g. How can we calculate things? Since there is no acceleration along y, the vx at any t will be the initial vx. The vy, since there is acceleration downwards, the vy t will be vy initial minus g times t. From this one, if we integrate again, you remember from the last lecture how to do this calculation. The xt will be vx initial times t, but we know the vx initial is the initial speed times cosinus theta. Sorry, I have a phone, just a minute. Give me 3 seconds, please. Oh, 3 minutes. Thanks. Thanks for your patience. So, you can see there is nothing from the x direction in the y, and nothing from the y direction in the x equations. So xt and yt, these are two independent motion. So we can see horizontally we move like a constant velocity motion, and vertically it's like a free fall. How can we use this information? For example, let's calculate the maximum height of the motion. This is the point A, you can see there. We know vyt equal vy initial minus gt. When will we reach this upper point? When the vertical direction becomes 0. How can I calculate it? I write 0 on the left and keep the equation as it come from the from the previous slide, and you can express t by vi sinus theta divided by g. Alright, so we know when will we reach this upper point, but we are only in the y direction. Go with this TA. Wow, that should be x, sorry. So here you have xt. Wait, no, it's not xt, sorry. It's yt, alright. So let's go back from the yt. Yt has an equation, what you solve by integrating twice the ay equal g acceleration plus the boundary condition. So, and we know how the y position changes with time. From the velocity, set it to 0. We know the TA when I reach the highest point, and I should write this TA into those t's. So yTA equal initial speed sine of theta times TA minus g over 2 TA square. So if you calculate it, you can see here I have a term vi sinus theta g. Here we have minus g over 2 vi sinus theta square. So the same terms, only the multiplicator here I have let's say 1, and here I have minus 1 over 2. And the height of the motion will be vi sine of theta divided by 2g. With the similar things, you can also calculate this distance along x. We can play with the game, we can play with the math, or we can play with the interactive simulator. Let me show you. So if you click on the link on the PDF, here, this interactive simulator, this is a link. You can get this page, and you can play a game, for example, changing the angle. You can change the initial speed. You can move it, the target, and you can fire, and you can play. Oh, here also you can switch on the air resistance or on off. So right now it's on, right now it's off, and you can see how the air resistance, for example, changes this projectile motion. So the speed was pretty high. Let's go down. Oops, that was too small. Seems too small. And if too much, yes, 2 stars. If you hit the middle of the target, you will get 3 stars. So you can play that game, changing the angle, or switch on and off the air resistance. You can see the velocity vector, the acceleration vector, force vectors. Or yes, that's all. You can clear the page. So this is a simple paper. So for example, can you tell me at what angle? So if you choose a let's say a 10 meter per second initial speed, which is switched off the air resistance. What is the angle and what is this x distance, this x range, and how can you reach the maximum x range at what distance? So probably you know that will be 45, but you see there are not that big differences between 45 and 50. So it's a very smooth function. So even if you go higher, this x distance will be not that high, not that large. All right. So what I will need for the next semester seminars: this measurement, use 5 walks, weight, walk up or down, weight again, walk upside down, and so on, and export it in Excel and bring it to the next seminar, and we will do the calibration, the fit, and based on your measurement you can say whether it's true that the pressure changes 12 Pascal in every meter, and we will do some example like this. Alright, that's all for now, and I wait another 2 minutes for questions, and otherwise we will meet on the seminars and you can ask real-time questions. Thanks for your patience. I stopped the YouTube live here and we can keep contact in Discord.